Yeah, so I will be talking about the Stage 3 ISS version 5.3 Level 2 data products changes and improvements. So the Stratospheric Aerosol and Gas Experiment, or the SAGE project on the International Space Station, is an occultation instrument that requires measurements of gases and aerosols in their stratosphere and upper troposphere. Currently, our data product for the Level 2 solar algorithm, we provide aerosol extinction products of aerosol extinction across non-channels, ozone, water vapor, and nitrogen dioxide. The current data product provides 3 different ozone profiles. We have the mesospheric ozone product, which is based on measurements within the Hartley-Huggins band. We have our MLR ozone, which is based on measurements made within the Chypre band. And in AO3, like the MLR ozone product, uses the Chypre band for calculating getting ozone measurements, but it actually uses a more Stage 2-like approach for simultaneous aerosol retrieval. And then finally, for our Level 2 lunar data products, we currently provide ozone, nitrogen dioxide, and nitrogen trioxide. We officially released version 5.3 of Stage 3 ISS data products in April of this year, and data can be found at the ASCC NASA website here. We also provide a data product user guide that will give more information on our products and other information that we provide within our data files. The brief summary here at first of what the significant changes to this version of our Stage 3 data product is. We added the implementation of a disturbance monitoring package data within our Level 1 solar algorithm to improve pointing accuracy. We changed our meteorological inputs, so we still use the MERA model data in our data processing. However, we moved from the 42 level MERA data product and up to a 72 level MERA data product for both solar and lunar algorithms. In 5.2, we introduced automated QA, and with this version, we have made some adjustments to make that QA process better. And then within the version change, we had some minor bug fixes within it. And also in 5.2, we turned off and removed several of our data quality flags because they were either not, they were broken and need to be fixed. So with 5.2, we fixed several of these flags and re-added them into the version 5.3 data product. So with our instrument being on the International Space Station, it poses a challenge due to the fact that we require accurate pointing knowledge and control for our instrument, but on the ISS, of course, you have visiting vehicles, attitude maneuvers, and other mechanical and vibrational disturbances that can add noise, especially with noise within our Level 1 transmission data. So to characterize these mechanical disturbances, a miniature inertial measurement unit built by Honeywell Aerospace was added to the payload, and it measures rotation in inertial space using ring laser gyroscopes oriented on 3 axes. So we took this data and used it only in the Level 1 algorithm to improve our transmission data to make sure we can correct for pointing errors when we have these disturbances in the ISS. For a much more detailed description of the implementation of the DMP, see Kevin's poster, I believe, on Thursday. So here's a plot showing how the disturbance DMP kind of works. So here, in the top row is our unbent transmission, and then the bottom row is without DMP, and the bottom row is unbent transmission with the DMP applied to the algorithm. So it's a transmission versus altitude. You have what we would consider a high disturbance event, then a medium disturbance event, and a low disturbance event. When pointing correctly for our transmission data, we would expect a value around 1 or really close to 1. So as you can see, without the DMP, you get lots of noise with in-out unbent transmission, which means our transmission is not, or the instrument is not being pointed correctly because of disturbances, causing transmission to be, kind of all over the place. And when you add in the DMP correction, you get a better looking transmission product. One of the other major changes is we changed from, like I said, in our meteorological inputs, we changed from 42 to 72 level MERA. One of the big advantages of this is we get better resolution. You get lots more data points, especially within the signal dominant portion of our altitude profiles. Another advantage of moving to the 72 level is the 42 level only went up to about 65 kilometers, and now we're getting meteorological input and model data up to about 78 kilometers. The big difference between the two, besides the increase in number of levels, the big difference between the two MERA data packages is that MERA 2 at the 42 level resolution use a constant pressure surface to map that data to, while 72 level MERA uses constant model levels. So now within the SAGE algorithm, we are interpolating pressure across latitude, longitude, and time to get it to match to the SAGE event latitude and times. We already do this with our other meteorological inputs, so we're just adding this for the pressure. Even with these changes, the meteor input change produced no significant product differences through the signal dominant and reliable part of the level 2 profile. Finally, the automated QA that we added in version 5.2. We have several criteria or triggers that can cause an event to be QA'd, including instrument errors, suspected blockages, or eclipses, among other things. Less than 1% of our solar occultation events are actually withheld. So here's an example of what was a withheld profile. So you have, this is a ozone number density for AO3 and MLR of both plots, and then you have aerosol extinction at 1021 nanometers. We had a trigger or a criteria that would remove events when AO3 and MLR differed around the ozone maximum. And before February 2022, there was only 2 of these. But in 5.2, post Hunga-Tonga eruption, we had 68 solar occultation events withheld due to the aerosol, increased aerosol extinction due to the eruption causing more noise within the ozone profiles, causing them to be, the maximums to be offset. So we looked at these events and determined they were still good, and we turned off this criteria, and those solar occultation events around Hunga-Tonga eruption are now within the version 5.3 data products that you can download. So I'm going to do, this is going to be a summary of the differences between 5.2 and 5.3. Changes between the version 5.2 and 5.3 had only actually minimal changes in the solar level 2 concentration and extinction coefficient in the signal dominant parts of the profile. However, these changes did show a decrease in product uncertainty between the 2 versions. Uncertainty differences can be attributed to the implementation of the DMP for reducing noise in the transmission, especially within the signal dominant parts of the profiles, which is between 20 and 40 kilometers. And you also had a reduction in the noise dominant part of the profiles as well. And since the only large change, or the only change really made to the lunar algorithm was the change in meteorological input data, there's no significant changes within the lunar level 2 products. So taking a look at the changes between the 2 versions, these are plots of altitude versus a percent difference between version 5.3 and 5.2. The blue line is mean, medium is black. You have ozone AO3 product and uncertainty, the HO2 product and uncertainty, and NO2 product and uncertainty. This is for the whole data set of from June 2017 through January of this year, and includes about 50,000 events. So, like I said on the previous slide, if you look at the middle signal dominant portions of the profile, you see there's really no change in the products here. But if you look at the uncertainty, you should be getting about this region getting about a 25% decrease in uncertainty in ozone, and around a 15% decrease in uncertainty in the water vapor product. And this is the same set of plots as previous over the same data set, but this time we're looking at aerosol extinction across all the channels. And with the other products, for the most part, I don't really see any large changes within the aerosol extinction. However, you do see a decrease of about, depending on the channel, about 20 to 25% in the aerosol extinction uncertainty within our signal dominant region. So this next plot, next few plots are just kind of showing off some of our version 5.3 data. So this is all the events from 10 degrees south to 10 degrees north from altitude on this y-axis from the beginning of our mission until mid-March. So this is aerosol extinction at 1021 nanometers, and you can within this data, aerosol extinction, you can see some events of interest. So you hear, you have the North Hemisphere wildfires, the Ambe eruption, Raikoki eruption, Australian wildfires, I'm going to butcher this, the Soufrière eruption, and then lastly, of course, the Hungatonga eruption, which can be really well seen in aerosol extinction, specifically since we have added back in those events that were previously removed from QA. And here's an example of the same plot over the same data set, the same latitude, or the same 10 degrees south to 10 degrees north, and in the water vapor again, you can see the Hungatonga pretty well. And then finally, just for an example, here's our ozone, which is the AO3 product across that same time period. So including the Stage 3 ISS version 5.3 algorithm has important improvements, especially for correcting mechanical disturbances. While there is minimal change overall, the data set quality is more consistent and has improved precision. Future work beyond version 5.3 may explore algorithm sensitivities for cases of significant aerosol layers within the stratosphere beyond what was seen on the previous Stage 3 meteor mission. Here's some contact information for some people in the Stage team, and with that, I'll take any questions.